Let's have a quick introduction to the key type of reaction in this chapter, the nucleophilic acyl substitution reaction. So let's compare ketones and aldehydes, right, from chapter 19 versus our carboxylic acid derivatives in this chapter. And I'm going to use the abbreviation CAD, right, for carboxylic acid derivative. So similarities between the ketones, aldehydes, and this chapter. Well, a nucleophile will add to the partially positive carbonyl carbon, right? A tetrahedral alkoxide intermediate will form. Okay? In both cases, that first step is the same. The differences are that carboxylic acid derivatives have a leaving group that's expelled as a stable anion, allowing for a substitution reaction to take place. Remember, a good leaving group is able to stabilize the negative charge that forms on it as a result. Ketone or aldehyde has no leaving group. We can only do addition. We could possibly do elimination of the oxygen as water, right? We saw that in some of the reactions, but we have no other leaving group present. So the carboxylic acid derivative has the leaving group, right? Here's the mechanism, like we saw before. Nucleophile adds, we have a tetrahedral intermediate. The O- comes back down, kicks out the leaving group, and we have a net substitution that's occurred. In an aldehyde or a ketone, we do not have a leaving group. So the intermediate that we get, whether it's from either one here, let's just draw it from the ketone here. By adding a nucleophile, we have something like this, RCO-. Here's the other R, here's the nucleophile, which can be protonated, and that's it. Okay? No leaving group attached there. So by virtue of this leaving group, it allows us to trade the nucleophile for that leaving group. For the different carboxylic acid derivatives, we can rank them in order of their relative reactivities. It tends to be that the addition step, so that first step of the mechanism, is usually the slowest one. So that's the one that'll determine the overall rate of this reaction. So if we have steric or electronic factors in that carbonyl, that can influence reactivity of the carboxylic acid derivative. So let's start with steric factors. If I have a carbonyl that is hindered, it will react more slowly. So hindered ones have bulky R groups nearby. If there is less substitution on the alpha carbon, remember the alpha carbon is the one next to the carbonyl. If we're unsubstituted, so if we have something like a methyl group next to the carbonyl, that will typically be the fastest if all we're changing is the substitution on the alpha carbon. Electronic factors actually end up being more important when we're considering the differences between all these different carboxylic acid derivatives. The reason for that is that strongly polarized carbonyls are more electrophilic. So we look at the leaving group, we use the same activating or deactivating rules that we used in the electrophilic aromatic substitution chapter. Okay? So halogens, remember, they deactivated a benzene ring by withdrawing electron density from it. Right? They make the carbonyl more electropositive, so that means that the acid chlorides are the most reactive. They react fastest with a nucleophile because the carbon is the most positive of all of them. We go over to the other side here, amides, right, and esters. Those lone pairs donate in by resonance. Okay? So that makes the carbonyl less positive. If we look at the electrostatic potential diagrams here, it's a little tough to see, but on the acid chloride, it's green. Over here on the amide, it's much closer to blue. It's subtle, but the reactivity is really fairly dramatic, the difference is. Anyway, now look at this here. The ester and the anhydride both have an oxygen next to the carbonyl. Why are anhydrides so reactive, whereas esters aren't? I'll give you a hint. In the ester, this lone pair of electrons donates in to the CO bond, kicking electrons up to an O-. That's a resonance structure. Overall, that OR is donating electron density in. In an anhydride, the lone pairs on the oxygen are in between two carbonyls. So these lone pairs donate much less. They can donate into that one and into that one. Okay? So overall, the electron donation, right, the donation of those pi electrons is essentially cut in half. And what ends up ruling in that anhydride is the fact that the oxygen is more electronegative. So it withdraws electron density. That oxygen is still as electronegative here in the ester, but it is overpowered by the donation of the lone pair of electrons that way. So because oxygen's lone pairs are tied up with resonance of that other carbonyl in the anhydride. In general, we say that the anhydrides and the acid chlorides are the most reactive, okay? That you can easily make any of the other ones from either of these two. So this chart here is not something that you probably need to concentrate on following these arrows with. Just remember that acid chlorides and anhydrides are the most reactive, okay? Way down here, esters and amides are the least reactive. So we can create anything below, anything lower in energy than what we started with, right? So as we'll see in this chapter, if we have a carboxylic acid, our C double bond O OH, that enters this whole equation by way of creation of the acid chloride. So that's a reaction we'll see coming right up. So very commonly we'll start with a carboxylic acid, make an acid chloride, and from there we can easily create any of the other ones. The reactions happen spontaneously, right? Delta G negative means it's a spontaneous reaction, right? That also means anhydrides can be turned easily into everything else except acid chlorides. That would be a non-spontaneous uphill reaction if we tried to make an anhydride into an acid chloride. It's specifically because of the very high energy reagent we use to make an acid chloride that we're able to enter at this very high energy state, like that. And generally, keep in mind, if we have an acid derivative, really any of those things, as long as it's energetically favorable, we can add a number of nucleophiles. There's usually just 5 of them that can react to form other functional groups, right? If I add water by the process called hydrolysis, we can go back to a carboxylic acid. We can really do that with most of the derivatives. Adding an alcohol makes an ester, right? And look, all you have to do is identify the leaving group and the nucleophile, right? In water, the O is the nucleophile, and the alcohol, the O is the nucleophile, and they just swap with each other, right? We have to have a proton transfer after the fact for these ones, right, in order to have a neutral oxygen, but we can do that. In aminolysis, N is the nucleophile. We replace that with the leaving group. In reduction, an H minus is the nucleophile, so that replaces the leaving group. Reduction can happen once, like this, to make an aldehyde, or twice to make this primary alcohol. Addition of a Grignard reagent once can make a ketone, or the Gilman reagent, right, R2CuLi, just to make the ketone, right? Grignard reagents typically add twice to make a tertiary alcohol. If I can stop at this ketone, I can then reduce that to get a secondary alcohol. So 2 R groups from the ketone and an H and an OH. So look how we specifically have access to creating a primary, secondary, or tertiary alcohol from most of our acid derivatives. Okay? That's very useful synthetically for us. But we also have access to all these other functional groups.